All right, this new operation, the factorial, given to us by that exclamation mark, is pretty useful when it comes to counting descending different opportunities, right? So if you're pulling cards out of a deck without replacing them, then the number of cards decreases by 1 every time. So let's work through a few factorials. 5 factorial, by definition, in fact, let's remind ourselves of the definition. N factorial is defined as n times n minus 1, so the next smallest number, or the next smallest natural number, n minus 2, and you keep doing this all the way down the line until you hit 2 times 1. And then I guess technically you can think of that as 0, and then the factorial moves along every step of the way, right? You can write n factorial as n, right? There's that n, and then n minus 1 factorial, because all of this is n minus 1 factorial, right? It's kind of like a cascading sort of picture here. You could write n factorial as n, and then the n minus 1, and then the n minus 2 factorial, because the n minus 2 factorial is everything past n minus 2. All right, but that was way too long of an explanation. Let's start solving some problems. All right, 5 factorial. So that will be 5 times 4 times 3 times 2 times 1. And when you go through this, you get 120. 8 factorial will be 8 times 7. In fact, let me write that as 8 times 7 factorial. It's also equal to 8 times 7 times 6 factorial, or 8 times 7 times 6 times 5 factorial. But either way, it's 8 times 7 times 6 times 5, 4, 3, 2, 1. All right, when you go through this, you get 40,320. So the factorial grows pretty quickly, right? 5 factorial was at 120, and if you go up just 3 numbers to 8, you get 40,000. Here, 1 factorial, 1 times, well, nothing, because the factorial ends when you get to 1. So that's just 1. And then 0 factorial, that by definition is defined to be 1.